Hi all, welcome you to live session. So let us just wait for a few other minutes for others to join. Yeah, mouse. Hi, I hope I am audible to you. Uh, Please reply through chat. Am I audible? Hello. Yes, now we'll start with the live session. So, welcome you all. Like only two participants, no problem. I hope like others are busy, but anyway, like whoever is interested will be joining soon. Let us not have just delay it further. We'll just kickstart with the session now. So, first topic is bias variance trade off. Okay, so we'll just see that. Okay. So now we'll just start with our session. So what essentially is bias? Bias is an error. So we'll just call it as an training error. Okay. We'll just see each and every point in detail. So first one, we'll just start with bias. So let me just quickly write up the agenda of today's session. So we'll just discuss about what is bias, then what is variance, then how to establish the what to say like a trade-off between bias and variance. How to establish trade-off between bias and variance. Also, we'll discuss about the term called overfitting, overfitting and underfitting. And also I'll be introducing different types of regression types. All are interrelated, so that's why I'm just explaining everything. Here I focus on linear regression, then polynomial regression. And also, in order to have the regularization, we'll have L1 and L2, which we'll call it as regularization, that is lasso and ridge regression. Lasso and ridge regression. So this is how you will have the different terms that will be discussed in today's session. So I'll just give you the various example. So what essentially is regression? Regression basically, I'll be introducing all the terms during my session. So I've just written the points to consider it as an agenda. Okay, for this bias variance trade-off. Then towards the end also we'll be discussing about performance evaluation with respect to classification. So first and foremost, we'll just have like this. Okay, so we'll just I'll draw one graph. So consider, okay, I'm just having one x-axis. Let me just hide this. Okay, so as to manage space. So I'll just draw one graph here. So I'll just have x-axis and y-axis. X-axis, consider I'm having age of building. Okay, I'm just having an house. I'm just want to have the age in building. I'm just measuring the age of a building in years. Then I'm having the price, associated price, which we'll call it as house price. Okay, so what will happen as and when the age of building increases? Okay, so obviously the price will keep declining. So it will just decline. Okay, so over a period of time, it keeps declining. Okay, so that is how you can very well have it here. So otherwise, you can very well have yet another example for this one. Like for example, you can have area, right? Area in square feet. I'm having area in square feet for x-axis, and always remember x-axis will be independent variable. X-axis will be independent variable, and y-axis will be dependent variable. Y-axis will be dependent variable. Here I'm just considering it as house price. The same way I'm having house price. So what will happen if area in square feet increases? Obviously, my house price also keeps increasing. So we'll just have like this. Assume I'm just having the a trend line here. So not exactly the same, right? It is just like the bent line. So which we'll call it as a parabolic line. So otherwise, if you just have each and every square feet increases, obviously my house price also will keep increasing. So in which case we'll call it as like a linear regression. So the same way, if I'm just having another example, so this is a case 1 and case 2, then case 3, if you consider, suppose assume I'm just having like this. Okay, number of years of service. Okay, service. or employment, whatever you can, if you want, you can consider. Then I just want to have the dependent variable. Dependent variable as income. So independent variable is service. Now I just have the data points. So I'm just having like this. Okay, you can very well see here. So it is like parabolic form. Suppose if I draw one straight line here, that will become a trend. And now if I want to measure, these are all my actual data. Okay, actual data, actual data, actual data points. And this one is my predicted line, predicted. So now what will be my error? Error will be the difference between the actual and the predicted. So suppose I am just measuring the difference. This is between this point, actual point and the predicted point. Same way I am just measuring actual and predicted. So same way I'll just consider this. Likewise, if I just consider finding out the difference between the actual and the predicted, then you will on finding the sum, you will have sum of squares, sum of square. Otherwise, if you take the mean of it, average of it, then I can call it as mean sum of squared error, mean sum of squared error. Okay, so otherwise we'll call it as MSE also, mean squared error. So now you can very well have the situation like this. Continuing further, later on I can revise also, so don't bother. So now I'm having another example. Okay, so in which case I'm just having height. Okay, this is considered as once again the independent variable, and the dependent variable could be weight. So, based on the height of a person, weight of a human also will be increasing. Naturally, it will increase, but some exemptions are always there. So, likewise, you will just have the uh, maybe after some age, like what will happen, like over a period, once they reach some proper height, maybe 5 feet for ladies or 5.5 for gents, it will stop growing. So that's how it keeps declining. So everywhere you can see the parabolic form. Okay, so otherwise age versus height, age versus height. So that also you can have it as a example. So you have the parabolic form. So in which case, going back to this example, the third example, the number of years and the income. So we have got the predicted and the actual, and we try to find the sum of squared error and mean sum of squared error also. So in which case, when you try to draw the straight fit or the trend line, it this linear regression always lacks the flexibility, right? Lacks the flexibility, since you will need to bend the line and make it as a parabolic one, so it lacks flexibility. Okay, so what do you infer from this? We have got large bias. Bias means error term. Bias means error. Okay, so always remember bias means error. So in which case you can very well have that you suppose assume the whole data set I'm having some 10,000 records I'm having. Okay, 10,000 records, total raw data set is 10,000 records, out of which I wanted to just divide the data into 2 by third. That was the thumb rule. Okay, normally people will divide the given data set into 2/3 for training, 2/3 for training data, and 1/3 will be considered as testing data. 1/3 will be considered as testing data. So that is how people will be considering. Normally they'll be considered. So in which case 7,000 will go for 7,000 will go for training, and 3,000 will go for testing. So that is how you will split the data into training data and testing data. But our problem here is, like when the for the simple linear regression for degree of polynomial is 1, you will always have the training data accuracy. Training data accuracy will be less. So why it is less? Since the bias, you have got large bias, right? So the accuracy of training data will be less. Okay, will be decreasing. Otherwise, if you just go for the testing data, when new point comes in to test our built model, then if you test for the testing data accuracy, then it will be more, it will be increasing. So that's how you will be having high bias here. So in this diagram you found high bias, huge bias is there. Okay, which is error in training data, error in training data. Okay, so that is how you can very well lab. Now always whenever we consider this x-axis and y-axis, we we want to get the relationship between the independent variable and the dependent variable. So even in this second case study also, as square feet area in square feet increases, the price of an house also tends to increase. Okay, so the same way as number of years of service in the third case study, number of years of service increases, the income automatically tends to increase. So as number of years go beyond a stipulated level, okay, so what will happen? They would have gained huge experience. The promotion that they'll get, that may not be that much soon that they expect. It will be stagnant. So after some period of time, like you, one cannot expect as much they wanted to have. So in which case the salary won't rise. So that is the reason you will have the parabolic way here. Okay, so now this is first case. The second scenario is, I would like to explain you the variance part. So in which case, consider the same x and y axis here. So I just have this service, number of years of service. Then I have the salary or income. Okay, so income is my dependent variable. So what will happen? I'm just having the parabolic curve here. Now I just have the different data points. Okay, so different data points. So when I just want to find out this, what will happen? I can very well go and connect all these dots. So what will happen here is I can very well join the different data points, the actual data points like this, which leads to overfitting. Overfitting. So in which case we can very well have only the small bias. Small bias. So this is case 2. So for I bias we have seen earlier. For this one, overfitting. So small bias in training data. Training data. Then what will happen to my variance? Variance, you will be having more variance. More variance. Okay, variance. Okay, so that is how you can have. And also, the degree of polynomial will keep increasing here. Degree of polynomial keeps increasing. That is the reason you have got polynomial regression. So this is an example of polynomial regression. Polynomial regression. Look at the curve that I've got it. Okay, so this is how you have got it. Now the sum of squares, if you just consider for this training data, you will be having very less values. So MSC tends to be less. Okay, the error seems to be less since you have got only small bias in training data. So we have seen two situations, one with the linear regression here, the linear regression, the case 3 example you can have. So this one is case 1 to explain different examples I've just given you, 1, 2, 3, 4, 5. See here, 4, 5 and all are examples to represent how well you will have the linear trend or polynomial regression. But the case 1 is related to the graph 3, which explains linear regression. That is, linear regression always lacks flexibility and hence you have got the large bias. So you have got huge or high error in training data, and thereby the accuracy will be less for training data. Whereas the testing data, the accuracy will be more. Same way, uh, you will have considered this case too. You have got the polynomial regression. Whereas here, the training data accuracy will be, it is totally opposite of this, right? So the training accuracy will be less the same way, and also you will be more, right? Since error is less, the training data accuracy will be more. Yes, training data accuracy will be more, and testing data accuracy will be less. Okay, since you have got small bias, training data accuracy will be more, and testing data accuracy will be less, since you have got huge variance. Okay, so it is exactly opposite of the previous one, but both are not allowed. Okay, you cannot have either a huge variance or a huge error. Okay, you need to have a balance between the error and the variance. Error is otherwise called as bias, right? So you need to establish a trade-off between bias and the variance. So that is the reason you will have another optimal curve. I'll just quickly explain you by drawing the same. Consider I am having this bias. Okay, so now you will have the error, the model. I'll just figure it out this, like model complexity. Write the x-axis name as model complexity, and the y-axis name is error. Okay, so what will happen if the complexity of the model increases? That is, from one polynomial degree, if it increases to 2, or if the degree of polynomial increases to 3, 4, etc. So likewise, if the model of complexity increases, our trend straight line will be uh, try to bend, and then you will have the polynomial regression. At the same time, you just see here the curve. Okay, so here you just see I'm having my bias now. So I'll just draw one graph. So now you, when my polynomial degree of polynomial is 1, my bias is more. That is what we have inferred from the case 1, isn't it? My case 1 is high bias, large bias. Okay, so that's why training a data accuracy is less. So now you come here. So first polynomial degree, if I've got, I'm just having high bias. Now once I just increase my model complexity, look at my graph, it keeps declining. Okay, it keeps declining. Okay, so that's how you can have like this. So this is called as bias. So earlier it was huge. As and when the model complexity increases, my bias comes down, error becomes low, bias will be low. Whereas here the bias will be high. On the other hand, if you just take this blue one, I'll just pick out. So here I am having variance now, variance. Okay, now I just have another dotted line, dotted line. So now I can have like this. Okay, so why I'm having, why I'm starting from the right? Here the variance, when the model complexity is more, my variance will be high. Okay, when the model complexity diminishes, my variance will be less. That is what we have informed from both the case 1 and case 2. See here, case 1, in the third graph, I have shown you very clearly the you will have only less variance. Okay, it will, high bias means huge bias is there, error is there, but you will have less variance. That is why the testing data accuracy is more. Okay. Whereas if you take up the complex model, okay, in which case you will have more variance, small bias. That's why you will have increase in training data, that is accuracy of training data will be more and testing data accuracy will be less. It will do well with the training data, but not, it will not do properly with the test data. Okay, so now going back to this, so the variance when it is high, see more variance, it will perform well with the training data and not perform well with the testing data. So that's how it start with the polynomial, that is variance is high, it then it keeps diminishing, and when the model is having a less uh, polynomial degree of polynomial, it keeps diminish, variance keeps diminishing. But this also is not an acceptable model or welcoming model, then in which case you need to choose an optimal model, so which is otherwise this line. Okay, this line. So I'm just pointing this. So this is called as the optimal one. Okay, optimal. Otherwise, I'll just take down this optimal model. Okay, so this is how you can very well achieve the optimal model. And this can be achieved by means of regularization. Regularization. And we have got the lasso and ridge regression to establish the same. Okay, there are 7 different types of regression, out of which we have discussed linear regression and also polynomial regression. The other one is lasso regression and ridge regression, with which you can achieve the optimal model. So this is how this diagram, you can call it as you are establishing a proper model or the trade-off between the bias error and the variance. So which we'll call it as, this one we'll call it as bias variance trade-off. Bias variance trade-off. So this is how you will establish the proper trade-off between the error bias and the variance. Okay, so this is what I would like wish to say for this particular bias variance trade-off. Okay, so now you can if anybody is interested, you can also make a gist of it. I'll also tell it in very many means. Okay, so MSE, okay, mean squared error, you can very well write like this: bias squared plus variance. This is the formula, bias squared plus variance. Otherwise, you can write it down. Bias is the difference between the prediction of the true model. True model is the population data. Okay, true model, and the average models, and how will you get this average models? That is, you will take the n samples from total population. So this is how you will have it. Now another way is bias of x can be given as f of x minus f dash of x. This is also possible. Another way, simply you can write it as bias is the inability of the model to be fit on the training data. It cannot perform well on the training data, right? So that's why I've given us inability of the model to be fit on the training data. That is called as bias. Then what is a variance? You will be amazed to know it, right? So what is variance? Variance is error in testing data. So in short form, you can remember bias is error in training data and variance is error in testing data. Okay, so that's how you can very well understand bias and variance. Okay, so this is a very, very important topic. Even if you get into machine learning or deep learning with neural networks or ANN, CNN, or whatnot, if, wherever you work on with algorithms, you need to understand how well you can establish the trade-off between bias and variance. Now, you can also just have it in other way down, like in nutshell, in nutshell, you can have low bias, low bias, low variance. You can call it as overfitting. Sorry, low bias and high variance. Okay, low bias and low variance is the balanced model. Low bias and high variance is called as the case one I have shown you, right? So that is how you can very well we can also see the overfitting in the decision tree and all, where we try to prune it, and then thereby you will get the proper decision tree. Okay, by setting the hyperparameters or by pruning, we can just avoid the overfitting in terms of classification. Okay, same way, if you have got high bias and low variance, which is called as underfit, which is the first one I told you. This is a second case study, overfitting we have seen. Okay, so the first one is underfit, high bias, and then low variance, underfit. Which one has to be avoided? High bias and high variance have to be avoided. So we always avoid this. Okay, so we always tend to avoid this. So please put a big tick into mark for this. Okay, either neither you cannot consider the overfitting or underfitting model, and this has to be removed. Then which particular combination have to be accepted? It's very obvious that you need to understand and accept low bias and low variance model. This is called as generalized model. Generalized model. Okay, so for this only we'll be using this XG boost or gradient boost or the different ensembling methods in order to just have both our training and testing data accuracy to be more. Okay, keeps increasing. So that is how you can very well remember this bias and variance in very many terms. Okay, now another way down, you can last way, right? Whoever is interested, you can very well take up to your choice. Okay, so high bias and high variance, you can very well call it as model is inconsistent. Model is inconsistent, and let me choose another ink for this. Model is inconsistent and inaccurate. Inaccurate and inconsistent. Okay. Whereas if I just consider high bias and low variance, then I can say model is consistent. Model is consistent but performs low on average. The third category could be low bias and high variance. Now, it is somewhat, you can say it is accurate, not exactly, right? Somewhat accurate and inconsistent on average. Inconsistent, stability will not be there. So that is why we say inconsistency, inconsistent on average. Now, same way, low bias, low variance. Okay, the fourth option, the model. So I'll just pick up the green color. So I just say model is consistent. Model is consistent and accurate. So that is how you can very well choose this particular combination, low bias and low variance. Okay, so that's how I wish to explain you this bias variance trade-off. Okay, let me also check the chat in between. Okay, if you have got any queries, please send it through chat. Okay, Please send your doubts through chat. Okay, so now we'll just move ahead with performance evaluation. So the next topic is performance evaluation, which we'll discuss in classification, in terms of classification. So there are very many terms. Once again, we need to discuss in this performance evaluation. So which I'll quickly explain you now. Before that, for this particular topic, you need to understand what is balanced data set, and what is imbalanced data set. Then you need to know about confusion matrix. Then you will need to know about accuracy score. Then you have to understand classification report. Classification report. See, for all these things, you have got the built-in, but I'm just giving you only the detail. I'm explaining the terminology behind everything. Okay, so where in Python you can really implement this confusion matrix, classification report, accuracy score, in order to judge the model. So where a classification report includes precision, then you will have recall, and also you will have FN score. And also I'll let you tell you like where all, under what context you need to just focus on precision, recall, F1 score, like that. Also we'll be discussing on the terms called true positive, true positive, false positive, then false negative, then true negative. So this confusion matrix will always have these four. Okay, so here if you just want to make a particular table, the matrix form, you can very well have like this. So you can very well have, first one is true positive, then false positive, false negative, then true negative. So this is how you can very well have it. Okay. So now you can very well have this true positive and true negative. So we will discuss how well you can have this true positive, true negative, all this stuff. So now I'll just go with one by each and every one of the terms that I mentioned over here. Considering the same way, data set, I am having some 10,000 records data set. This is the data set I am having in full. Okay, so I'm getting a raw data set with the 10,000 records. Now it is having a target variable where it will classify two classes, that is two group classification, dichotomous classification. So it will have 1 or 0. Suppose, in which case, assume I am having 7,000 records is classified as 1, and 3,000 records out of this 10,000 records, I'm just having 7,000 to be classified as one category, and then 3,000 records I'm categorized as a 0 category. Now it is not proportionate, right? So it is having different proportions. The proportions is not equal, it is 70%, 30% here. So in which case we'll call these type of data set as imbalanced data set. On the other hand, you just take 10,000 same record data set. This time you got 5,000 here and here 5,000. And 5,000 represents one category. And then this 0 represents, that is 5,000 represents, another 5,000 represents 0 category. So in which case, this sort of having equal proportions, I can call it as having equal proportions, I can call it as balanced data set. This is how you need to understand with unequal proportions. Balanced data set is unequal proportion of classes in the group. That is target variable. Okay, unequal proportions of data. Whereas here you have got equal proportions. That is why we claim to call it as balanced data set. So for that only, we, in order to have the equal proportion between training and testing data, also in Python we'll use the parameter called stratify equal to y. Okay, so that is the option that we'll set it. Okay, stratify equal to y. Now we'll just go ahead with the explanation. So I'll just draw one table, like we'll take one case example. Okay, now we'll just take one example. Now I'll just consider some 10 different values, 10 values, or pictures or images I'll take. Okay, so I just have actual, which I'll call it as truth value. Then I'll call other one is predicted. Now, like I'm interested in garden. Okay, so I'll just consider I'm having various flowers at my home. So what will happen? So I just take the truth image as flower, and the not truth as some other picture. Okay, so you will have different combinations. I'll quickly explain. So for flower, I just give it as F1. Okay, then F2 also is flower. Then F3, basically it is also a flower. Then suppose assume I'm having another image as bird image. Okay, this is the bird. It is not a flower. Maybe this one is flower image. This is also flower, this is also flower. Three flower images I've got, and the fourth images is bird. Then the fifth image I just take it as like any different thing. Okay, so assume it is representing some machine. Okay, some machine it is just representing. Okay, V1. The next one is I just consider F1 or F3, right? I just put, then F4 I just say this is also a flower. Okay, FLR is flower. Then the same way I consider H1. It is a image of a human, image of a human. Then the seventh one I consider, see, F1, F1, 2, 3, 4, 5, 6, 7, right? Then I just consider C1, C1 as my computer image, image of a computer. Then the next one I can have F5, okay, F5 and F6. F5 and F6, all F's are my flowers. Okay, so there is a flower image, this is also a flower image, this is also a flower image, and this one is also a flower image. Okay, whereas the other than F are called as different other than flowers. It could be bird or a machine or human or computer or whatnot, anything, any image you consider. Okay, and otherwise instead of already we have given computer here, so what I do is I'll just consider this as an animal. Okay, animal. uh, okay, so I'm just having animal here. I'm having animal. So other than this are bird, animal, human, and computer. So four different images I've got. Now let us. These are all the truth values, actual values. Now I am having the predicted value. Now assume I'm out of any one of you. Like if I just ask you, like since I've told this F1, F2, F3 are all flowers, and B1, V1, H1 and C1 and other than flowers, you can easily predict, right? Suppose assume I'm just asking one kid. Okay, so what will happen? First case is just predicting it as flower. So it is correctly predicted. Truth also, actual is also flower, and the person, the kid also is predicted as a flower. The same way, second image I'm showing, F2. That also it tends to be floor. He is correctly predicting it. Third one also is correctly predicting. So three correctly predicted cases are there. Now for B1 is it is bird, but is wrongly predicting it as flower. Okay. Now the same case for V1 for animal also is predicting it as flower. Okay. And then for human it is predicting it as flower. Okay, so in which case now we'll consider, I wish to explain you the true positive, false positive and all. So that's the reason I have taken down this working example. Now my intention is to tell you what is true positive. So true positive, how many are true positive? True positive, see always for truth you need to associate either true or false. Maybe for predicted you need to associate positive or negative. This is a thumb rule so as to remember it properly. Okay, so in which case I just want to find out the true positive. So here flower, actually it is flower, and here also it is flower, so it is true. And then flower, for this case also it is true. The same way, any other one we have got a flower here. The last one you just take, otherwise this fifth one, right? Fifth one, the kid is finding it as flower. Okay, so in which case this is also flower, this is also flower, truth is also flower, the person is also credited as flower. So in which case this is true. So out of 10, how many are this one? We cannot, we have to just consider how many true positive cases are there. Both are coinciding. True. True, actually, it is true. Predicted is also true. So, true positive. True, you need to associate for actual. True or false, you need to associate for actual. For predicted, you need to associate positive or negative. Positive or negative. Okay, here you need to assign true or false. If you remember this, you can very well remember the formula also. So both are true here. True positive. So in which case, how many true positives are there? 4. So same way, you take up the false positive. False positive, FP. FP is denoted as false positive. In which case, you have the value as 3. See here, B1 is bird, but he is predicting as flower, which is false. V1 is animal, he is predicting as flower, which is false. H1 is human, he is predicting it as false, which is also false. So FP is 3. Okay. Now, what is left out now? This F4, C1, and F6. These three out of 10 is left out. Okay. Yes, out of this you have got this many. So now 10. Yes, so you have got these many to be so yeah, 4 plus 3 you have got 7. So only 3 is pending. So that we'll just find out right now. So now the TP value is 4 and the false negative. Now false negative you need to find out for this. Okay, so now we just have the false negative for this case as 2. False negative is 2. For this, probably for this and this, you just consider as false negative. And then true negative, you just consider this. Okay, so in which case you will have false negative as 2. And then what is true negative? True negative is 1. So likewise, now we have achieved TP as 4, FP as 3, TN as 1, and FN as 2. Now we got another formula to understand, which is otherwise called as recall. So now before that, before getting into this classification report, first let me explain you the accuracy score. What is the accuracy score? Accuracy score, accuracy score. Okay, so you can very well use this score for whenever the data set, okay, whenever the data set balanced data set, when the data set is balanced, we'll always please note down accuracy score is a best measure to use when we have got balanced data set. When you have got balanced data set, then accuracy score is the proper measure. But you can ask me, when you have got imbalanced data set, then what score you need to use, right? Then we need to get into this one, what to say, classification report. So which encompasses precision, precision, recall, and FN score. Okay, now let us quickly discuss what is precision, recall, and FN score. And before that, with the example that I have shown you, let me just show you how to have the formula for accuracy score. Accuracy score is given as TP plus TN upon all. What is all for? TP plus FP plus FN plus TN. TN. Okay. TN. Total negative. So TP plus FP plus FN plus TN. Okay. This is TN. True negative. So now you substitute. What is TP? TP is 4. 4 plus what is TN? TN is 1. Okay, divided by what is TP plus you can substitute all the 4, right? So you just substitute here 4 plus what is FP3 plus FN is 2 plus TN is 1. On summing up, we know already the total is 10, but what is the numerator? It is 5. So 5 upon 10, you get 0.5. So 50% is the accuracy score. Okay, so this is how you can evaluate the accuracy score. But the classification report, the extension of it, but it is used for imbalanced data set. So what is the formula for precision? That we'll see now. Okay, I'll just choose the green color. Precision formula, you can very well have like this: TP upon TP plus FP. Okay, so here what is TP? The TP value is 4. And what is FP? 3. So you just say 4 divided by 4 plus 3. Okay, so you will get on solving you will get 0.57. So 57% will be my precision. But what is precision? Please note it down. Precision is out of all flower predictions in our case, right? Out of all flower predictions in this example, out of all flower predictions, how many is correctly predicted? Correctly predicted. Out of flower cases or predictions, how many is correctly predicted? Okay, so that is how you can very well have. So out of all flower predictions means what? How many cases where you have got seven, right? So you have got 7. So that's how you got 4 plus 3, 7. And out of 7, you got 4. So 4 by 7 will give me 57. And hence it is precision. So precision is out of all flower predictions, how many is correctly predicting it as flower? Okay, now the next one is, we'll call it as recall. This precision is also called as specificity. Okay, specificity. And then now we'll just discuss about recall. Recall is TP upon TP plus FN. TP plus FN. Now you can have total positive is 6, Then Fn, let me check. If it is 2. So Tp is 4. So 4 plus 2. So on solving, you will have 0.67. So we have got 67 percentage accuracy. Recall. And what is recall? This is other way down. You can call it as TPR, true positive rate. Okay, true positive rate. Okay. Now you can say this term recall as sensitivity. Sensitivity. The other name for recall is sensitivity. Okay, now you can note it down. What is recall by definition? Out of all flower predictions, flower actuals, out of all flower actuals, how many are correctly predicted? Correctly predicted. This is actuals. Okay, actuals there I have given you predicted. So out of all flower actuals, how many are correctly predicted? So that is how you can very well have the definition for recall precision. Now why you need to have this uh, fn score, fn beta score of fn score? Fn score, see, always remember, when I told you when to use accuracy score. Accuracy score is meant when you have the balanced data set. Okay. When you have the imbalanced data set, then you need to use classification report. But in the classification report, when to use precision recall and F1 score, that also we need to discuss. Before discussing, we'll also discuss the formula. Before discussing this, we'll just also see what is F1. Okay, so F1 score. F1 score is the harmonic mean of precision and recall. Harmonic mean, harmonic mean of precision and recall. Okay, other way down, you can very well write the expanded formulas. 1 plus beta squared times precision multiplied by recall divided by beta squared multiplied by precision plus recall. So this is how you can, other way down, statement wise, you can say F1 score is an harmonic mean of precision and recall. Now, when to choose, that we'll discuss now. When to choose. So we'll just use this right now. So when to use Fn. So Fn is very important. Fn is important. When Fn is important, then we use recall measure. We use recall measure. The same way, when FP is important, FP is important, then we can use precision. Then we use precision measure. When both are important, okay, when both are important, both are important, I'll just write neatly. Both are important. Then only we need to use F1 score. Okay, got it. So this is how you need to remember. When F1 is important, then we have to use recall measure. When Fn is important, we use recall measure. When false positive is important, we use precision measure. When both are important, then we'll use F1 score. So F1 score, by default, it is an harmonic mean of precision and recall. So this is how you can very well have. Also, this confusion matrix, you just have it here. So TP plus TN, right? So TP plus TN divided by all four will give you accuracy score. Then FP divided by this column alone will give you this false positive rate. Then true positive rate is like this, TP divided by this column alone. So likewise, you have got many formulas, but accuracy score is TP by TN, TP plus TN divided by TP plus FP plus FN plus TN. Okay, but what is false negative? Thus, that also I would like to tell you before I close the session. So I'll just give FP. FP is otherwise called as type 1 error. Type 1 error. And then FN is otherwise called as type 2 error. Type 2 error. Okay, and which is found to be serious? Type 1 is found to be serious. Okay, is considered as serious. Come to type 2. So type 1 error is more serious than type 2 error. Okay, so type 1 error is more serious than type 2 error. So always remember, false positive is called as type 1 error and the false negative is called as type 2 error. Okay, so this is what I wish to tell you or share my knowledge to you in this live session. Okay, so let me just also tell you one another thing, like last one. Okay, so what is true positive or type 1 error? So type 1 error is rejecting null hypothesis when it is true. When it is true. And then what is type 2 error? Type 2 error. Type 2 error is failing to reject, that is accepting. In statistics, we will not say rejecting, we will say failing to reject or fail to reject. Okay, in which case we will call it as accept. So failing to reject null hypothesis when it is false. When it is false. So this is how you can remember type 1 and type 2 error. Okay. So in today's session, we have discussed about bias variance trade-off. Before summarizing, uh, let me just explain you this. Yes, we have discussed about bias variance trade-off. So we have discussed what is bias, that is in terms of error, training data error. Variance is testing data error. And then we need to establish a trade-off between bias and variance. Then what is overfitting and underfitting? Okay, so that and all we have explained with different examples, and considering the main example could be case 1 here, the graph 3. So number of years of service as independent variable and income as dependent variable. We have just drawn a parabolic curve and tried to map the trend line by finding out the difference between the actual and predicted. The difference, we have summed up all these values, which is MSE, and finding out the average mean squared error we found out. Okay, and here it tend to be more here. The large bias is there. So that's how we have got the problem of underfitting here. We got the problem of underfitting. Okay, underfitting. That's the reason training data is not performing well, will be less, whereas testing data accuracy is more. Then I bias, that is error in training data. That is the reason I told you large bias. Then the next one is we have discussed about the polynomial regression, where you have got only small bias in training data but more variance in testing data. So that's the reason we have got the training data accuracy is more and testing data accuracy is less, and then overall MSE is found to be less. Error is less. And since we could establish the connection between all the given points, it tends to overfit the model. Okay, that's how you got more variance here. But we cannot prefer to opt for either high bias, high huge variance, or high bias, low variance, or low bias, high variance. You need to have only the low bias, low variance optimal model, which can be established using regularization or lasso or ridge regression. Also, you can increase the data set in order to have the proper optimal value or model. So both the ways, either by applying a regularization technique with L1, L2, or by increasing the data set, you can very well have the optimal model. And then this also we have discussed about the trade-off, how to establish the balance bias variance trade-off here in order to have the balance between bias and variance. Then we have also discussed MSE equal to bias squared plus variance. Bias is the difference between prediction of the true model and the average models, and bias can also be given as f of x minus the predicted one. Then bias is the inability of the model to be fit on the training data, whereas variance is error in testing data. In nutshell, LBHV is overfitting for classification, HBLV is underfitting. HBHV you should not consider, you should avoid it, whereas LBLV both should be low. Then only you need to consider, which we'll call it as generalized model, which can be achieved using XGBoost or grid search CV. Many different ensembling methods are there where both training and testing accuracy will be improved model. So high bias, high variance is model is inconsistent and inaccurate. High bias, low variance is model is consistent but low on average. Low bias, high variance somewhat accurate and inconsistent on average. And low bias, low variance is model is consistent and accurate. So this is the green color one is the acceptable model. Low bias and low variance is the acceptable model. Then the second topic is performance evaluation, where we have discussed about equal proportions balanced data set, unequal proportions imbalanced data set, confusion matrix with four quadrants TP, TN, FP, FN. Then FP is type 1 error, which is serious error compared to type 2 error, and FN is type 2 error. Then TP plus TN divided by all four will give you the accuracy score, but accuracy score can be applied only for balanced data set. Then for imbalanced data set, we need to use precision, recall, and F1 score. But when to use precision is when we have got this particular one. Okay, precision. So precision, we have got the formulas TP by TP plus FP. Then recall, the same way we got TP divided by TP plus FN. Then also we have just seen F1 score is the harmonic mean of precision and recall. So when to recall measure should when Fn is important, then we need to use recall measure. The same way when Fp is important, then we'll use precision measure. When both are important, then we'll use F1 score. When both are important, we'll use F1 score. So that's how you need to understand both the topics. Okay, I really welcome the various comments in the comment section. I hope you all have enjoyed this session. Okay, I'm sure about it. So please like, subscribe. Those who have not subscribed already, please try to subscribe. And I really tend to do the various uh, live sessions in near future. I'll send you the confirmation or the link or the invite as soon as I tend to do it. Okay, and please post your whatever the way that you have liked the sessions. Okay, please post it in the comment section, or also give like. Okay, that's all I would like to extend as of now. So thank you all for your patience listening. I was expecting more crowd, but since this is the first session, I'm having five members, but that too, this is a very wonderful start that I'm having it here. Thank you one and all for your patience listening. Let us just connect soon for other lecture, similar lecture very soon. Thank you.